In this video, we're going to look at the R value of insulation. Then we're going to define the overall heat transfer coefficient, which is sometimes referred to as a conductance. When we considered a resistance network to look at heat transfer through a wall, for example, here where we have a conduction process, and a convection process, we used potentially area-specific resistances in order to calculate the heat flux through that system. Let's focus on the conduction resistance, conduction area-specific resistance, R2'2. The definition of that area-specific conduction resistance is the thickness of that material L over the conductivity of that material. Let's look at that value. The units for this area-specific resistance are kelvins meters squared per watts. This is exactly what is meant when we talk about an RSI value. If you go to the hardware store and look at insulation, you can probably find somewhere on there the RSI value, and that is the R value in SI units. It is identically our area-specific resistance defined as L over K. In North America, much of the insulation is still referred to using R values. The R value is in British units, which means that the R value is in units of degrees Fahrenheit instead of Kelvin, feet squared for the area instead of meters squared, and British thermal units for energy. And in order to turn an energy into a power, as we have watts in the SI unit, we divide that energy by hours. And so the R value that you see on a package of insulation is actually units of degrees Fahrenheit feet squared hours per BTU. Strange thing to do, but it gets actually worse than that. Sometimes we talk about the R value per inch, and that's perhaps practical if you're going to the hardware store and your insulation is sold in terms of R value. If you express it as R values per inch, you can determine what R value you get by how many inches you stuff into your wall. Let's think about the units on that. So all we've done is we've taken our R value in the British units and we've divided by inches. So now we have very strange units. Of course, we have feet squared for our area and inches for our per unit length. A real mess, as with many things in that system. But let's look at these units. Think about the thermal conductivity. In SI units, the thermal conductivity is watts per meter Kelvin. Well, this is actually the inverse of that in very bizarre units. So if we take the BTU by hour, that will give us the watts, and that's on the bottom, or it give us the equivalent. It's a unit of power, as is watts. And if we look at this being an area divided by a length, that will give us units of length, and it's on the top. So that's equivalent dimensionally to the meters in there. And of course, the degrees Fahrenheit is equivalent to the degrees Kelvin. So the R value per inch is actually the inverse of the thermal conductivity expressed in extremely bizarre units. Finally, I'd like to talk about the overall heat transfer coefficient. When we calculate the heat flux using a resistance network, or the heat rate, sorry, we evaluate the heat rate in watts as a temperature difference divided by the total resistance, summing up all of the resistors in our system. If you recall, in convection heat transfer, we have Newton's law of cooling, where we have a convection heat transfer coefficient multiplying an area and a temperature difference. Sometimes it's very convenient to write our heat rate as in a form that's very similar to our convection equation. And so to do that, we note that we could write that Q is equal to U, which we'll define here and call it our overall heat transfer coefficient, area times T times a difference in temperatures. Now this looks exactly the same as this, except what does U have to be in order to make this so? U is simply the inverse of the R total times the area, or the inverse of the area-specific resistance. So we can collapse our whole resistance network into a single overall heat transfer coefficient U and use it exactly as we use Newton's law of cooling in any of our calculations. And because now instead of a resistance where we're dividing, This is the inverse of the resistance. It multiplies this. U is sometimes called the conductance for our system.